Hello everyone. Thank you for the EHES and the organizing team for inviting us to present Numina. Numina all started, with a challenge, which is going now, way too far. Just to give you some background about what we're going to talk about, a quick intro to Numina. I'm going to focus a bit on what we do right now. So we're doing AI for Math Olympiad, which of course, may sound, trivial or very far from research consideration, but actually it's a great playground actually to evaluate, emergent reasoning capabilities of LLM models. And then I'm going to conclude with more like forward-looking statements for Numina, but also broadly speaking, what is called ASI, so artificial super intelligence. So Numina is it's an open project as an organization, so we're a non-profit organization. It's an open scientific international collaboration. We have contributors, from Europe, China, the US. It's not, easy every day, these days in the current context about, AI research, and that's something really super important. First and foremost, it's a project by and for people who are passionate about math and that want that math remain an open domain in the age of AI. So that's why everything we do is open. So open models, open data sets, and we open all the code of what we do. We are supported, by many actually companies from the industry, from XTX markets as well. Which is our main contributor. Just a few numbers. So we started the project 1.5 years ago, and now actually it's growing pretty quickly. So we have a community of more than 70 people, full-time research scientists of about 7 people, 15 part-time contributors. So by part-time we mean people that contribute more than one day per week to the project. Mostly we have graduate students, PhD students contributing to the project. We have about 4 million euro in budget, in cash budget. Most of the budget we use to collect data, and then our model is to go partner with some companies to provide us access to computing resources. We have one ongoing research partnership with an AI company based in China called Moonshot AI, which is providing access to up to 1,000 H100 GPUs. So that's what we name as the compute resources. So all in all, we operate with a budget which is close now to about 10 million of resources, which can seem, a lot for math, a drop in the ocean at the scale of AI and reasoning. It's a bit, it's a paradox. Anyway. I'm going to start with a few words about, what we've done over the last 18 months and where we're going as an organization. So it all started with this, Progress Prize. I'm sure, you're familiar with the International Math Olympiad. Last year, a prize was announced for the first open source AI to reach the gold medal at the AIMO. And because, they thought that no, organization or no AI, at least no open AI, would be able to reach this level, they organized an intermediate prize with, let's say, national Olympiad level types of problems. Okay, problems of a lower difficulty, and we participated, and that's how we started. Actually, when we started Numina, with Gia in particular, my co-founder from the previous company we did together. First and foremost, Numina was a way for us to get up to speed with LLM. We had spent 10 years before doing mostly computer vision for heart disease diagnostics. And I think like many people in our field, we were a bit shocked, by the progress of LLM and the ability not only to deal with language, but to see, emerging patterns of reasoning, and doing math was just a great way to get there. So that's how it all started. So we won this prize, actually, 6 months after the foundation of Numina. And we decided, I'm going to cover this a bit later, to set a new goal for this year, which is to build the first open source, open data set model that can reach the gold medal level at the International Math Olympiad. So that's our current focus. So what we did last year, so we won this prize. We solved 60% of the problems on the private set of a national level Olympiad. There is an important remark here, which is all the problems had integer solutions, and integer solutions between 0 and 999. For example, if the problem was to find, let's say, a polynomial function, you had to estimate p at 20, for example, and to output this result. It is an important consideration because there is a real key question about the ability to assess reasoning at scale. The great thing, with integer solutions is you have a unique representation, which is a good fit for LLM. But as soon as, for example, you're dealing with fractions, for example, you can have multiple representation of the same thing, right? And that's a real challenge, which is still an open question. Even frontier math, a PhD level, math reasoning benchmark, twist also all the output into integer solutions. We believe that formal math, we'll touch upon this later, for formal mathematical languages such as Lean or Coq or Isabelle, is a great way to be able to build pure, let's say exhaustive reasoning benchmarks. But today we need to keep in mind that at least as of last year, and still some ongoing benchmarks still rely on integer outputs to evaluate reasoning. So basically you only evaluate the outcome, not really the entire process. Anyway, so what we did last year, we took an open source model from, I think it was DeepSeek. And we did 2 passes of what we call supervised fine-tuning. So you take a large LLM and you specifically instruct the model to solve math problem and solution. So what we did last year is we collected a large data set of competitive math problem and solutions from the internet. So we browsed literally the entire internet for archives of Olympiads from Russia, Eastern Europe, China. This is where we found actually most of the data, as well as Europe, US, etc. And we built a data processing pipeline to do OCR, so optical character recognition, and to extract everything from the PDF, to do also automated segmentation of the PDF. I'm not going to get all the details of what we did, but this is really the dirty, this is the bulk of the work in ML. That's really how we get things done. So without giving all the details, we did 3 things. So pure regex, for the easy to parse problems. We had also set up a pipeline of manual segmentation in China. So we literally paid people to box, with their mouse PDF. And we also tried to use the LLM to do it. But it didn't really work back in the days. Basically, the middle ground between humans and regex, it was just too hard, for LLM and too easy for humans, so it wasn't easy to deal with. Anyway, so we built this data set of math problem and solutions. We instructed specifically the LLM to solve, to do problem solving of Olympiad level. And we did another pass of training, which was to use what we call tool integrated reasoning. So we trained, that's a framework from Microsoft. And basically, we trained then this model to learn how to call SymPy, which is a library of symbolic resolution. And you can think of what we did last year as building an agent that can do some sort of reasoning to math problem solving, and to learn to call SymPy, pretty much as soon as possible. That was very relevant last year because, again, pretty much all the problems had integer solutions. So calling SymPy, was a great way to get there. But as you know, to get to the step, the next step, so to international math Olympiad level, to another level of proof, you need to make proof, not just to output or to find the right integer solution to a problem. And for this, this approach, that was our winning approach last year, was of course not sufficient. So we released in open source after the competition the entire data set, which became actually the largest ever publicly released corpus of math problem and solutions with 860,000 entries. NVIDIA actually has released since then a corpus of, say, 5 million rows, but actually there's only, I think, 300,000 problems. So I guess there is still an open debate. Is it still the biggest? I mean, not that it matters, but at least as of last year, that was by far the largest release of a corpus of math problem and solutions. We were very pleased to see that the LLM community has used extensively this data set. You know, there is a metric that you can use to try to infer, to retrieve the training intensity. So how much, you know, your data set was, you know, used in an LLM. And very quickly, sorry, the community has used it. So which was very satisfactory for us. A few days after the competition, so we do this first pass, you know, we win the progress prize, we're happy, you know, we get the prize from Theorem in Bath, and like 2 days later, Google DeepMind releases Alpha Proof, and they reach a silver medal at the International Math Olympiad. Great job. And the main difference between what we do in Alpha Proof is not only the level of difficulty, of course, but also the fact that they use formal math to be able to make proofs, basically. They used a pipeline which is relatively similar to AlphaZero, the AlphaGo types of algorithm, which is basically a tree search type of approach, and you're trying to learn basically 2 functions to navigate optimally the different steps. One is a policy function, which is basically how to generate the optimal next step, and the value function, how to evaluate optimally where you basically where you stand, basically the value of the generation you just created. There is a couple of caveats. There's a couple here. One is these, you know, tree search step prover type of approach are, I mean, quite expensive in terms of inference. That's something which is important. The second thing is, and sorry, I'm going to detail a bit, perhaps the parallel between, you know, chess and Go and math. You know, in chess, the state of the game is basically the state of the board, and you have an exhaustive, you know, representation of the next possible steps, which are all the possible moves that can be played. And you can think of a proof pretty much the same way, as the state being the sequence of lines. Basically, you have your problem statement, which is formalized, and each action, like each tactic that you used in formal language being one step. So you can represent formal proofs in a similar fashion as exploring as a Go or as a type of game. And actually, Guillaume Lample and actually François Charton here in the team at Meta was also actually has also pioneered this approach a few years ago. So they did an amazing job, but you know, when we met with the community, we felt that the feedback was, you know, it's amazing, but at the end of the day, it's a blog post. You know, we have never seen the model, and even if we had access to it, you know, the amount of compute needed to run this kind of model is just not practical. So that's why we decided to, you know, to set a new goal for Numina after the Progress Prize, and to make it more than just, you know, let's say a learning journey, and to build an AI model able to reach the gold medal, which is fully open, so open source with open data as well, and also to pursue a formal math approach. We started, I'm going to touch upon this later, by trying to reproduce the approach of Alpha Proof, but we found out, as you know, a few weeks later, after this summer, OpenAI released O1, and then, you know, DeepSeek R1 and all the OX, you know, type of model which are doing deep chain of thought, and they were able to reach actually a performance at, you know, math problem solving in pure natural language that was far beyond what we thought was possible even a few months before. So what we decided to do, and I'm going to develop this, and that's our current research focus, is basically to blend the approach of Alpha Proof with formal math and the approach of deep chain of thought with you know, in the O1 like. Anyway, so Our first goal for this year is to build an AI model that can reach gold. We need to build a huge formal math data set to get there. We're also going to pursue our effort in informal math. And Frieder, who is in the room here, is actually working on this and leading this effort with us. So thank you, Frieder. Mostly because, again, the capabilities of LLM using purely natural language actually have gone far beyond what we could have predicted last year, and we believe there is still a lot of room to grow these capabilities. We have also set an objective to release, let's say, not just release things for the AI community. Again, I mean, our vision is that math is and should remain an open domain. We have released, a huge corpus of math problem solution, but it's just basically a data set, a dump on Hugging Face, which is not super practical, for anyone who's not, a machine learning engineer. So that's why we have decided to build a web platform to enable the broader community to interact with our data set, to try to sketch proof and to get some feedback. And we should be actually able to release this at least privately as a starting point in a few weeks. So getting into what we've done over the last few months to get there. First, we had to build, and we're still building, a pipeline to create a large corpus of formal math. And so we're doing two things. One is we're doing manual annotations. So we're literally paying, lean experts from all around the world to spend some time and to formalize math problem, problem statements and solutions. That's one. And we're also doing auto-formalization. So we're basically just doing campaigns where we launch an auto-formalization algorithm, which is trying to do it automatically. I'm going to give a bit details about the challenges of both approaches. Of course, manual annotations are extremely expensive. I touch upon this in the next slide. And one of the issue we found is we really have diminishing return. Basically, to formalize an international math Olympiad proof, it can take between 6 and 12 hours of human labor to an expert. And the amount of tokens produced after hour 2, hour 3 becomes more and more smaller, and we need a lot of tokens to train the algorithm. Also, we found that when we started working with formal language, we had a bit of the naive, we had a lot of naive thought in general, but in particular, we have the naive thought that if, the statement and the proof compile, then we're good. I mean, we found that it's a bit more complex than this. I mean, there are many ways, to develop a proof, to write a proof that compiles. And in particular, we had issues of alignment, which means what we give to annotators is a problem statement and the proof in natural language, and it's a translation problem. But sometimes, it's much more efficient to use a different chain of thought in formal language, just so because you can call the right function or the right library in formal language. And so we ended up, with proofs that do compile, but for which the reasoning was not aligned at all, or barely aligned with the proof in natural language, which so job done from the human standpoint, but actually wasn't super. It was a bit counterproductive actually to train the model. So what we're doing right now is we're capping basically the time per problem, and we're asking our human annotators to leave what are called sorry statements, so blanks in the proof. And we found it to be much more effective, both from a productivity standpoint, also from a consistency standpoint, because we have less variations of style, if you'd like, from one annotator to the other, which helps also train the AI. Auto-formalization. So we're using auto-formalization and manual annotations on different set of problems. Typically, we're trying to do auto-formalizations on problems that are much, let's say, simpler. We're trying just to get volume, from this campaign. We have been able, in theory, so that was of last February, to auto-formalize in principle, up to 150,000 problems and solutions. In reality, this is an upper bound for one reason, which is the auto-formalization of the statement is far from being perfect, and sometimes it makes the solution trivial. So there is a lot of waste actually in these 150,000. So the true number should be in the tens, probably in the tens of thousands today. I tried to make this graph up to date, but for some reason PowerPoint was not with me this morning. So as of today, we have formalized manually 15,000 problems. That's a significant budget. I mean, today to formalize 2,000 problems per month, we spend in the order of 100,000 euros per month. So that's like 50 euros per problem. So that's a huge budget, and that's where most of our budget is spent today. But that's necessary. Just wanted to give you a quick view of our formalization platforms, which we developed in-house. I mean, we aim to open source everything. It has not been open source yet, but it should be. So it's a platform we developed for our own annotators, and basically in which they can get access to a queue of problems, of tasks, basically of problems to be formalized. So at the top, you have the problem statement, then you can get access to some solutions, and you have an editor to start writing your formal solution, and you can get feedback from the compiler. Now they also have access to our own proof completion AI, to our auto-formalization AI as well. This is still a work in progress, and we'll see. I mean, what will be the outcome of this in the future? Because using your own IDE to do the work also, I mean, can do the job to some degree. We just felt it to be convenient, in particular, to do reviews actually, because we were doing a manual review of the job of the annotators. Anyway, so we did an intermediary release of our natural language corpus. I'm speaking under the control of Frieder, but we plan to do the major release for this summer to grow the corpus. And it should be in the order of 3 to 4 million problems. Do I get this right? Oh, yeah? In the ballpark, still the right number, okay. Which we plan to release after the Olympiad this year, along with our formal mass data corpus as well, which we will release as well, of course. So as I said, when we started last September, the goal was to reproduce a step prover type of approach, an alpha proof type of approach. We were really impressed by the capabilities of the O1, DeepSeek R1 types of approach, and we felt like there was a bit of a risk. I mean, can this model reach the same level of alpha proof? But if they do, that was our assumption, our bet. It has a lot of advantages. One is, let's say, the readability of the proof. By blending so what you see on the right, this is a chain of thought pattern. Basically, the algorithm is trained to blend the natural language reasoning and the formal reasoning. And by doing this, the advantage is you have a better visibility and readability of the output of the language compared to a step prover that just spits a formal language proof. That's one. Two, in principle, this should be much faster in inference and much more, cost effective in inference, as we don't need basically to do the tree search. So you can think of kind of compiling different nodes, using natural language, taking shortcuts somehow compared to step provers. And so the question we had, when we started is this going to scale basically and to be able to reach the same level of alpha proof? And the answer, so we're not there yet, but we believe the answer is yes. So we released Kimina a few weeks ago, and so this is the blue curve. The sample budget is sorry, for context, so MINI F2F is like the kind of formal reasoning benchmark reference. And because, it's formal NAS, you have the problem statement formalized, so you can, try to do several generations and to see how many generations from the model do I need to have a proof and a solution that compile, basically. And this is what we call the sample budget. Basically, how many samples do you allow the model to generate to find a solution? And what we showed is that this approach clearly outperformed all the state, the existing types of approach, in particular the step proof type of approach. Alpha proof is not in this. We don't have access to the model, right? But in principle, this model was trained using less than 500 GPUs, so that's at least one order of magnitude less than what other models have been using. So we're really confident about the ability of this approach to scale and to reach basically at least a silver medal level. I did not precise, but when DeepMind reached the silver medal, the gap between the silver medal and the gold medal were combinatorics problems. One of the main reasons, presumably, is that it's because the combinatoric libraries in Lean, the formal language that they use, are not as developed as in the other languages, which makes the proofs, not just writing the statement, but writing the proofs much longer. To give you an order of magnitude, it should take about 250 lines, low hundreds of lines, to write a formal math proof of an AIMO problem. While for combinatorics, with a proof, at least I've seen, take between 1,000 and 1,500 lines. So it's like 5x longer proofs because you don't have the libraries or the functions you can call, which kind of makes sense that it's harder for the models to get there. But it's not like a conceptual limit. It's an engineering problem, presumably. So we have started to see human-like style. It's a good thing of, by doing this alignment and blended chain of thought between natural language and formal language, you can also force our annotators, to follow the same reasoning path, which also helps with the alignment. And we see, we have very nice, scaling laws between the size of the models, the amount of compute which is sent, and right now, our main bottleneck is access to compute. So kind of my job, the organization for the next 2 months, is to get access to orders of magnitude more of computing resources. Yes?
Maybe you said it and I just missed it, but the KiminaMath, what kind of models do you start? Is it a pre-trained language model with reinforcement learning, or is it some other sort of? Yeah,
exactly. So the goal is we take a pre-trained model, which instruct that do it math. And what we do is we're doing, sorry, I did not mention this. We're doing deep reinforcement learning at scale with long chain of thought. So the same approach as the O1.
So reward just success in.
Yeah, exactly. So at the tail, I'm going to show a demo, but and thank you for pointing this out. I did not explain. At the tail of the chain of thought, there is the entire formal block. And so what you can do is reinforce, basically your reward is basically between tags, we output the entire formal block, and we can do reinforcement on this reward. Actually, we can use several rewards. One is, does it compile? There is also a metric in Lean called the heartbeat, which is, I understand, like the stress you put on the compiler, which can be an indicator of to which extent do you brute force or not your way. And you can also use, for example, the number of, the heartbeat as a reward as well. But yeah, the main idea behind this approach is deep reinforcement learning, using long chain of thought and using the formal block at the tail of the chain of thought as a reward. That's the main idea. Actually, I can show you a quick demo. So there is an online demo for those of you who are interested. It can only do, like junior or Olympiad type of problems. So, but to give you a sense, so here you can input a problem in natural language, you have access to the auto-formalizer. So the model outputs the formalization, it checks the syntax, and then you can either try, if you feel lucky, I mean, you can try pass at 1, and otherwise you can just directly call 16 generations of the model. It can take, you know, probably up to 1 minute, so I've run it before. And what you can see here when the reasoning is complete, you have your 16 generations, the one for which the lean validation failed at the end, and the ones for which the lean validation succeeded here. Okay, and this is a formal reasoning block, and you have the access to the entire chain of thought that blends the natural language and the formal language. So this is available at demo.projectnumina.ai. And to give you a sense of the time it takes, yeah, it's probably going to take a couple of minutes for 16 generations. Also, we don't have a lot of GPU running the inference, so the we could scale this up if needed. Okay. Sorry, that was a slide I skipped actually, where I explained the chain of thought and the final lean code, and the difference between the step prover type of approach. We did the demo. All right. So now, looking forward, we have like 15 minutes left or so. We so you know, last year, so we won this Progress Prize, and you know, 2 days later, DeepMind released a silver medal. This year we released a KiminaProver, we reached state of the art on MineIF2F, and 2 weeks later, DeepSeek releases a DeepSeek Prover v2, which reached 89% on MineIF2F, and that's, you know, that's both, I mean, the beauty and, you know, the doom of this field is like, you know, is like it's your models, you know, it's even worse than, you know, fresh fish. I mean, the main difference between DeepSeek Prover and our approach, to be honest, is just the amount of compute. I mean, they have access to at least 1 order of magnitude of compute more than we do, which is a bit frustrating for us. But I mean, that's what we're trying to sort out by the competition. I hope we'll get there. So now what we're really trying to do is to scale up the training to compute. We also know that DeepSeek Prover has used a larger model as a base, a more capable pre-trained model, also because they had more compute, right? So there is an obvious, you know, improvement, you know, point for us, which is just like to throw more energy at the problem. So that's one. And two, today our model does not interact with the lean server during the chain of thought. So it does not validate, you know, the intermediate lean generation, which is also kind of a low-hanging fruit of improvement. And now, you know, the International Math Olympiad is in 2 months, and we're also starting to think of the roadmap post AIMO. I mean, we think that, you know, morally, let's say AIMO level difficulty of reasoning difficulty is within reach of this approach. I mean, so now the question is how we can start to also make something useful for the mathematical, you know, for the math community. I've listed, you know, some of the challenges and what, you know, the field, you know, is actively thinking of. One is, I'm going to start by, so auto-formalization is really the key, because today one of the gaps of lean is the fact it's really incomplete in terms of coverage of, you know, math research. So that's the #1 problem to solve. I mean, to get towards professional math with formal approach is to have a bigger corpus and also functions and libraries that the model can call, and it's a virtuous cycle. You know, that's one. I'll touch upon this later, but we believe that lemma lemma proving should be in reach to some degree. I mean, there should be, and we've started to collect actually some of these lemmas, technical lemmas that don't require theoretical overheads, that should be formalizable using the current capabilities of Lean, that should not require, let's say, a creativity or a cognitive power which is, stronger than, a gold medal IMO, which should be in reach. So lemma proving may be a low-hanging fruit to start serving research, and I get there a bit later. We know that some research teams are also working on auto-decomposition. We don't work on this today. The idea of auto-decomposition is, given a theorem, can I generate automatically the blueprint of a proof, which means the decomposition of a proof into lemmas. That may be a completely different type of algorithm where you just try to learn a representation of a proof as the dependencies between the lemmas. And so these are really, I think, from a pure, let's say, generalist standpoint, let's say the active topics of research, so auto-decomposition, auto-formalization, or auto-informalization also, I mean, translating from Lean to natural language, and lemma proving. Now, and I will finish with this, there is still a question which is, what does creative thinking mean? I mean, and what does, to which extent do we consider that we will start to have reached some sort of super intelligence in math? The move 37 of AlphaGo was really the emblematic move of Go, where, for the first time, we witnessed a move that was not only unique, but also creative. And so there's one question, which is, what does this look like for LLM, and what does this look like for reasoning at math? So I will finish with this. But first, yes, I mean, we are starting to work on technical lemmata. We believe this is right with the continuity of what we've been doing with Olympiad. So we're looking for statements that do not require specific domain knowledge or theoretical overhead and are considered, solvable, to some degree, right? Like not collapse, for example. So I'm going to give you a couple of examples. One is that we have found or have been shared by mathematicians. One on, an article from 2018. This is, a technical lemmas in trying to find, I think, geodesic, or to count geodesic of maximal length on a hypercube. Another one is from an article called Approximate Union Closed Conjecture. These are typically like technical lemmata, that are, used, in mathematical research, and we believe that this should be within reach of an algorithm which is able to reach the gold medal at the AIMO. So what we're trying right now is to build data sets of this kind of lemmata. From public research, published research, but also. If you know mathematicians, or you want to contribute, with lemmas that are still open, or that you're still working on, that's something we love to hear about, because that's the best test set for this kind of. By nature, it's not contaminated, so that's this is probably going to be a pillar of our roadmap post IMO, is to start to build towards this and to try to at least make ourselves useful, to mathematicians as quickly as possible. That's one. And I'm going to close with just a general remark about what we call ASI, artificial superintelligence. So this idea that we could basically build a machine that can be, let's say, more intelligent. Whatever that means. This than all of the humans. That's really the very definition of superintelligence, is this idea that the machine is going to be able to do things that even the best of humans in the field will not be able to do. Before getting this, I just wanted to take a step back. Of course, we can be skeptical about, the hallucination. We can be skeptical about, what AI can and cannot do today. We should, and on this graph, from Leopold Aschenbrenner, I don't know about, I'm not going to make claims about the future, the forward, part of the curve, but there is something which, we should always keep in mind. It was like a few orders of magnitude of compute ago, actually no more than 5 years ago, these models could barely generate a sentence that made sense. I mean, it could barely generate a consistent statement, right? 5 years later, 10 to the 8, orders of magnitude more of compute, we're getting to models. So Gemini, 2.5 Pro was announced yesterday. They were able to solve half of the US Math Olympiad problems in pure natural language. So as far as we know, I mean, they did not disclose, but they did not use formal language, including proofs, at the first try. I mean, so the progress in the field has been, dramatical. We can make conjectures about, is it going to explode or not? There may be also diminishing returns, which means as we get, more and more discoveries, the marginal, likelihood or the difficulty to make new discoveries is going to increase. But the progress over the last 5 years has just been phenomenal. So, and this part is more personal, but in my this view of artificial superintelligence compared to the definition stated before, I think there should be also a conception of amount of energy used, and that's basically the difference between brute forcing a problem. Sorry about that. So that's the difference between brute forcing a problem and finding a clever solution. I mean, if you give infinite amount of energy, of compute or time, yeah, for me, like, we're not going to be on this curve of superintelligence. So there's got to be an energy constraint in the creation of intelligence. This level, so superintelligence using a limited amount of energy, has been achieved already in narrow domains. It has been achieved at chess, at Go. I think it's fair to say it has been achieved in Euclidean 2D geometry, as alpha geometry is able to solve the Olympiad problem in 6 seconds. That's probably, better than any human on Earth. And this idea about, AlphaGo was this conception of a move that was creative and unique. And if we look at the different narrow domains where superintelligence has been achieved, so being better than the best of humans using a limited amount of energy, what these, domains have in common is, given a state, the state of the game or the state of the proof, the entire universe of the next possible actions is exhaustively known. So basically, the model has access to the entire universe of what can be done, and reinforcement proved to be very effective and to outperform the human capability. So now, it's actually a bit different from what we do using LLM for math, because we're using the LLM as a generator, which means the possible actions that are attainable, touchable by the LLM, by definition come from the pre-training, from what the LLM contains, right? The LLM does not, the system doesn't have access to all the universe of all, that can be written in principle. But the beauty of LLM, it should be able to write its own action. It should be able to write its own definition. And that's a behavior we have not observed yet. That being said, no later than last Friday, Google released AlphaEvolve, which improves the Strassen algorithm for matrix multiplication. And what is, quite unique in this approach is they did not, as far as I know, probably they did not use formal math or formal reasoning to make this breakthrough. It was basically an evolution. Basically, they did mutation to the code, and they had access to a verifier. Basically, they ran the algorithm that was generated by the system. And I think there is a couple of lessons here which are important. That we probably don't need, in principle, formal math or formal reasoning, or even guarantee of reasoning, to make breakthroughs in problems in the kind of find X such that. Find a new algorithm such that. Find a new protein, for example, in biology, such that, which means I believe it's probably in these classes of problem, instances of problem, that we're going to see the real, let's say, super intelligence breakthroughs. So ability of the machine to discover things or new knowledge or new science, which is beyond, what we have been able to find with humans. Because, even if the reasoning is wrong, if you have found X such that, you have solved the problem. And it's really different from the proof that, kind of statements and types of problems. Unless, you can twist prove that, to find a counterexample, to some degree. But for the prove that kind of problems, you need to test the process, not just the outcome. And you're probably going to need some sort of formal language to be able to make a breakthrough in this. And I'm going to finish here. So I think we can reasonably, in math, but also in other domains, expect AI improvement to state-of-the-art, really new knowledge, kind of new discoveries for problems, in the kind of find X, such that, assuming we have a low latency, very scalable verifier. Typically find a new algorithm, for example. And that's achievable without formal reasoning and without new moves. Some are new, paradigms of reasoning. I believe that that's probably where we're going to find pretty much immediately AlphaEvolve, being a first instance, a lot of discoveries in the short term. Formal math seems needed, and I'm insisting on the seems needed to tackle proof generation. Formal math today has a huge gap, which is the coverage, of research math is still relatively low. So compared to the algorithms that only use natural language, it's a bit lagging behind in terms of capability. That being said, so today, formal math basically has a bit of a cold start compared to models dealing with natural language, in particular for the find X, such that types of problems. But the beauty of formal math is, if you manage to formalize an entire field, this is the only way for the machine to do self-play and to generate its own validation at large scale. And so that's why I think we don't know to which extent there's going to be an alignment, of the development of AI using formal math versus AI using natural language. There's probably going to be faster discoveries of pure natural language without, formal verification of the chain of thought in the short term. But on the longer term, if we want, I think, to truly bring, in particular, abstract fields forward, we're going to need, we're probably going to need formal math, because it is the only way to just throw compute at the problem at scale. And so last, and I'm going to finish there. There's a bit of a question, at least that keeps bugging me, perhaps not the community, but what should be the equivalent of move 37 in the field of reasoning of mathematics? And you can think of it both ways. Basically, one, make an analogy which no one has thought about before between two concepts and which makes sense to resolve the problem. I think this is the equivalent of move 37. And we've heard a lot of people saying, these LLMs, they just do sophisticated pattern matching. Reasoning by analogy is sophisticated pattern matching, and it actually can go quite far. So I think we should not dismiss or consider just sophisticated pattern matching. That's actually an emerging, I think, a very deep and profound emerging reasoning capability. I think the main question will be how elegant or how far are the objects, in the analogy. And I think that probably perhaps the power, the more distant they are, at least in our own human representation of these objects, the more powerful it's going to become. And of course, the last thing is, today we're still waiting for LLM to put a new word on a new concept, or a new definition. And I think some people, they expect move 37 to be this, define a new abstraction, define a new object. I think that's even a more the step ahead, because it means that move 37 was you keep playing with the existing rules. You have just found a new path using the existing rules, while writing a new definition means that the algorithm will have found a new action in the game. Basically, it's like you have found you're playing the game of math, and you're now able to write new rules, and that's probably even another level. Voilà. Sorry, that's supposed to be over. Thank you.
Thanks. Great talk. Maybe time for one or two questions.
Yeah, so apparently in AlphaGo, they found out that when you don't give the machine any human-played games, and just let it self-play, it's actually better. Is that possible for mathematics, to do complete self-play, give the rules?
It's a great question. I think we're probably going to see it maybe emerge in geometry first. Alpha geometry, the same way that alpha geometry, was released before. I mean, I don't work for Google. I don't know what they're doing. I'd love to know what they're doing, but I don't. Okay. But for alpha geometry, they design a domain-specific language where the algorithm learns to make constructions. So it's probable that while using the LLM, we still have this question of the action space is kind of limited by what the LLM can spit, basically. So I think it's maybe in geometry we should be able to see this pure self-play type of evolution and the discovery of new concepts. And from my understanding of AlphaGo, the beauty of it is, along the training, they were able to see the machine discover new openings or new tactics. And they were able to find, tactics that were known and that were, or the sequence, let's say, the order in which the machine discovered concept was kind of aligned with the same way the humans, sophisticated their game over time, up to a point where, the machine just started to discover things that were far beyond our understanding. In the case of math, and I hope we'll see it, but you can think of it as if we're able to design a system in which the machine can do self-play, it'd be also super interesting to see, the sequence, and the order and how, the machine starts to discover the concept. And does it follow the same path, for example, as we did?
Yeah. Let me comment. I can't resist because I've given talks on this topic. So there's a missing thing, a big difference with AlphaGo and games, which is that math is not just about producing statements and their proofs and definitions and so forth, because there's an algorithm for that. You can generate them, enumerate them all. It's finding the interesting ones. And so there has to be some way the machine can measure or judge what's an interesting statement. That's very primitive. There's really very little work on that problem. There are people, for example, David McAllister is a computer scientist who has proposed NAV0, this idea, has worked on this quite a bit, but there's really very little work on it at this point. So that's the missing ingredient.
Today is not part of the reward, it's not part of the reward at all.
Even to define what is an interesting statement, it's not trivial.
Yeah, exactly. Even for us, I don't know if even us, at least I don't, but if you have an opinion of what are the characteristics.
Yeah, I can show you the talk.
So I have to see that.
Yeah, on your last thing on move 37, you make a difference between discovering a move and discovering a concept. Don't you think it's closer than you think? Because somehow if a machine managed to find a move somewhere in the representation of the machine, the latent representation, there was some kind of structure that enabled this move. So maybe the difference between the great move and the concept is just a problem of interpretability, which is a different branch but a quickly growing branch.
I don't know. That's probably beyond my understanding. I think what keeps bugging me is this idea that we're still yet to see the machine, but not just in mathematics, perhaps even just in social sciences or domain where like the machine manages to put a name to a concept. That's something which seems to be very human. It seems like, in neuroscience, like human is still, at least to our knowledge, the only species able to put a symbol to a concept. And so there is this question about the ability to put a new sequence of symbols to a new idea or to a new concept, which is not something that we have, at least as far as I know, witnessed, and maybe we're missing something here. In the case of math, if I do, always need to be super cautious about making, the parallel between the human brain and AI. Some, it comes and goes, basically. But my understanding in the human brain, for example, like math, kind of reasoning kind of activation sits in the spatial representation and geometry, not in language, basically. So maybe there is also something missing there, at least in our model representation, is the ability of the model to deal, with spatial representation or geometry. Actually, Lean is starting to support geometry. And I believe it's a very exciting development, as if you can have a unified language to teach the model, spatial representation and concept, and reasoning in language. Maybe we'll be able to unlock this kind of new reasoning. But it's pure,
But would we be happy if we had a way to see the concept, something we can define as a concept in the model, and we, the human, get to give it a name. The machine doesn't give the name, but we would be happy. The concept would have been defined by the machines, so long we can clearly identify something in the machine that corresponds to this concept.
It's a fascinating discussion, but we have many speakers.
Thank you.